Okay, in this video I'm going to talk about free space loss for our wireless course, and we're interested in particular in things like 2.4 gigahertz radio waves and 5.7 gigahertz radio waves for our Wi-Fi. What I will do is I'll show you the equation that's given, for example, in your text on Cisco wireless, CCNA wireless. But I'm also going to show you where that equation comes from, sort of starting from fundamental principles. And this is, a good exercise in seeing where things come from and using a little bit of the math that you've taken over the years. And so the equation, the loss in dB, decibels, is a function of both the frequency and the distance, say the distance between transmitting and receiving antenna. And this is for free space, so it really applies out in space, satellite systems, but it will be the basis for our understanding of loss in terrestrial systems here on the surface of the Earth. For example, our Wi-Fi. So the loss as a function of frequency and distance is 32.4 dB plus 20 log base 10 of the frequency given in megahertz plus 20 log 10 of the distance given in kilometers. Okay, and so FMHZ is equal to frequency in megahertz. So for example, 2,400 megahertz would be our 2.4 gigahertz Wi-Fi. And DKM is the distance in kilometers. Okay? Where does this come from? I'll show you. The basic idea here is that what we're doing is we've got an ever-expanding sphere of energy. Basically, the amount of energy put out per unit time, that is the power, is spread out over a sphere. In the simplest case of an isotropic antenna, which is what we're considering here, which sort of pumps out spherical electromagnetic waves. As you go to twice and then 3 times the radius, okay, so this is then the radius r, and this would be 2r, twice that original radius, and this would be 3r. You can kind of draw a picture, and I don't know how successful I'll be at it, where you have sort of this little patch of area that the electromagnetic waves are covering. And if you go to twice the radius, out here, the same patch now is 4 times the area. Okay, so let's see if I can draw this. We're going to have 4 times the area here that we have here when we go to twice the radius. Okay, and when you go to 3 times the radius, you have 9 times the area. So maybe we could go all the way out to here and sort of try to draw the same patch now has expanded to be 9 times. So what's happening is that this same little bit of energy is now covering larger and larger areas. Okay, and this is the origin of the inverse square law. This is the inverse square law. And what we're going to find is that the power is a function of the radius, that is the distance from the original isotropic antenna, is proportional to 1 over r squared. Okay? And let me go ahead and make that a little bit clear. Okay, so the idea is that we're pumping out electromagnetic spherical waves, and the energy associated with that spherical wave is spread out over the surface of a sphere. And as the sphere gets larger and larger, the surface area over which the same amount of energy is spread out over an ever-increasing area, an area that increases as r squared. And therefore the power, which is the energy, you can think of it as the energy per unit area on that sphere, is going like 1 over r squared. Okay. In any case, it's an inverse square law, and in fact, with a point source, we can write that the power at the receiver at a distance r from a point source transmitter is equal to the transmit power times lambda squared, where lambda is the wavelength, divided by 4 pi quantity squared r squared. So this is the inverse square law. R is equal to the distance of the receiver from the point source. Okay? And this represents the inverse square law. Okay? What I'm going to do now is I'm going to say, look, we're interested in received power in decibel units. All of this is in watts or milliwatts at this point. Lambda is the wavelength. I better define that of our EM, our electromagnetic wave. Okay? And what I'm going to do then is I'm going to take the log of both sides of this equation, essentially. But first I'm going to rearrange it slightly and say, look, our normal loss in decibel units is equal to minus 10 log base 10 of the received power over the transmit power. Okay, this is how we calculate loss in decibels. And the minus sign accounts for the fact that we want to have a positive loss when the received power is less than the transmitted power. But when the received power is less than the transmitted power, I'm taking the log of a number less than 1, and that's always negative. And so I put this minus sign here to give myself a positive loss value. And so now we can go ahead and continue this equation plugging in for the ratio PRX over PTX, which when I rearrange, I just bring PTX to the denominator on the left here. I just get this lambda squared over 4 pi squared r squared. And so we can write this as minus 10 log base 10 of lambda squared over 4 pi quantity squared r squared. Okay? And I can continue this, and I'm going to use the laws of exponents and the logarithms, and recall that the log of a over b is the log of a minus the log of b, and the log of a times b is the log of a plus the log of b. And so, applying that rule, I'll take this completely apart. Let's see here. What I'm going to do is I'm going to replace also, I'm going to say that the speed of light is meters per second lambda times the frequency, okay? And I'm going to rewrite lambda as c over f. So let me do that first. Minus 10 log base 10 of c squared in the numerator over f squared. And I'm going to go ahead and put 4 pi and just allow for a c squared over 4 pi quantity squared here. And now I've got 1 over r squared f squared. Here we go. Okay, so you can verify the algebra on that. And now I'm going to apply the log rules here, and I'm going to say that this is minus 10 log base 10 of c squared over 4 squared pi squared minus 10 log base 10 of r to the of 1 over r squared minus 10 log base 10 of 1 over f squared. Okay? The other log rule I'll be using is that the log of a to the x is equal to x times log of a. Okay? And so I'm going to rewrite this as, well, look, this is just a quantity. We can literally plug this into our calculator, and we're going to get minus 147.6. Okay? C is a number. C is 3 times 10 to the 8th meters per second. Pi is 3.14. We can just calculate that. And now I'm going to say that this is 1 over r squared is really r to the minus 2 power. And so I'm going to get that minus 2 power, which would be the exponent here, x, and bring it out front. And I'm going to have a minus 2 times our negative 10 to give us a plus 20 log base 10 of r. Same thing with the f squared in the denominator, plus 20 log base 10 of f. Okay? Now I'm going to use the fact that the radius, or the distance in kilometers, times 10 to the third is equal to the radius in meters. Meters are our fundamental unit here. Everything is in meters and watts and meters for wavelength and all. This is the fundamental physics of it. So r is currently in meters and f is currently in hertz. But I'm going to switch them over to the units I like, which are kilometers and megahertz, more commonly used in wireless systems. And I'm also going to say that the frequency in megahertz times 10 to the 6th is equal to the frequency in hertz. And the frequency I have currently is in hertz. And so I'm going to go ahead and write minus 147.6 plus 20 log base 10 of r in kilometers times 1e3, 1000, plus 20 log base 10 of, and I'll have to put my parentheses down here, the frequency in megahertz times 1 million, 1e to the 6th. Okay? And once again, I'm going to use the fact that the log of a product is the sum of the logs. So here I have the log of a product again, and don't forget I've got a 20 out front. And so I'm going to write now minus 147.6 plus 20 log base 10 of 1e to the 3 plus 20 log base 10 of r in kilometers plus 20 log base 10 of 1e to the 6th. This is from the frequency there, plus 20 log base 10 of f in megahertz. But just a second here. Taking the log base 10 of a power of 10 is very easy. The log base 10 of 1e to the 3 is 3. The log base 10 of 1e to the 6th is 6. That's the definition of the log. So this is minus 147.6 plus 3 times 20, which is 60, plus 6 times 20, which is 120, plus 20 log base 10 of r in kilometers, plus 20 log base 10 of f in megahertz. And now you can see this is 180 minus 147.6. That is 32.4 plus 32.4 plus 20 log base 10 of r in kilometers plus 20 log base 10 of f in megahertz. And this is great. This is the loss in dB as a function of r and f. Okay, so you can see where it comes from. And what I'll do now is show you a couple of the nice properties that this equation has. First of all, if the frequency goes to 10 times the frequency, the loss goes to the loss plus 20 dB. Why is that? If I multiply the frequency by 10, I end up with a log base 10 of 10. I can basically take apart that product. That 10 becomes a multiplier on the inside of the log, and it becomes a 20 log of 10 when I take it apart. So increasing the frequency by multiplying it by 10 leads to a 20 dB increase in the loss, in exactly the same way that increasing the distance by a factor of 10, the loss increases by 20 dB. Okay? That's great. The other really nice thing about it is that the loss in decibels of D equals 1 kilometer and F equal to 2400 megahertz is just 100.0 dB. And so when we're at 2.4 megahertz, as if we're using 2.4 megahertz Wi-Fi, then I have 100 dB loss at 1 kilometer. Using the rules over here, if I want to go to 100 meters, I will decrease. Well, if I divide the frequency by 10, the loss goes down by 20. Divide the distance by 10, the loss goes down by 20. So multiplying either the distance or the frequency causes the loss to go up. Dividing either the frequency or the distance causes the loss to go down. Okay, so I could say the frequency going to 1/10 of the frequency, the loss goes to L minus 20 dB. Okay, in any case, what happens here then is we can take this 100 dB, instead of 100 kilometer or 1,000 meters, we can go to 100 meters and get 80 dB. We can go to 10 meters and get 60 dB. We can go to 1 meter and get 40 dB. And so it's a very easy sort of thing to remember that at 1 meter and at 2.4 gigahertz we have 40 dB loss. 10 meters, 60 dB. 100 meters, 80 dB. And 1,000 meters, 1 kilometer, 100 dB. So there's a great equation, and it allows us to see where everything comes from. Starting with the inverse square law of physics and understanding that we're taking the same amount of energy and spreading it over a larger and larger surface area as the wave expands. Okay? So this is this equation. It's in the CCNA wireless exam, and you should know how to plug it into your calculator. And I hope this helps.